Wonderful. Thank you all for your time and your attention. I'm going to talk about some work that I did with Hossein Azarbanyan from Elsevier. And from this long article title, I really want to hone in and pique your curiosity on the idea of discovering data sets. So the article will be a bit technical, and so I'm going to try and stay at a high level for time's sake, but I really want to think about how we look for and what data sets look like in text, and what are some approaches algorithmically that we can look at to find data sets, and what we can do together in the future to find them more effectively. To set up the problem, we looked at the Coleridge competition Kaggle data, which is 14,000 documents paired with data sets. The data sets are known, but the location of the data set within the document is not given. We looked at the first, second, and third place submissions to the competition. Each submission took a unique approach, and we further develop and refine these approaches and find that their unique approaches all benefit and work together well as an ensemble, and that in practice, using everything is the best idea. To motivate this and sort of think about the problem at a high level, I'm going to show some examples of how data sets might be cited in the text, with some examples from actual articles from the Kaggle competition. So a data set might appear as its explicit name. So you might have your data set name or generically data set name. And some examples of that from actual articles are the rural-urban continuum codes, or the Census of Agriculture, or North American Breeding Bird Survey. So you just have your data set name and exactly as it appears in the text. This would be ideal and easy, but as we know, it's a little more complicated. Less commonly, your data set name could be wrapped with maybe quotation marks, as you can see in a couple examples here, which is a small thing, but if you're not careful, these can cause you to miss some samples that you care about. Very commonly, long data set names will appear with an abbreviation or an acronym associated with that, and we can see that in a couple examples here. This is very common, and a couple of the top submissions hone in on this pattern to help their models. Now we're going to start getting into less common or more complex references, right? So you can have a data set with some different acronym, and that can be mixed in the order of the data set reference. So you could have a beginning post-secondary students, its acronym, longitudinal study. So here the acronym is mixed in, and then you have survey of graduate students and postdoctorates in science and engineering, but abbreviated only with GSF. So in the assumptions about the structure of the reference and its associated acronym, we have to. Some other examples that add complexity are maybe baccalaureate and beyond longitudinal, where now it's only abbreviated B and B, and has been replaced with an ampersand. Coastal change analysis program has a dash included. And interestingly, optimum interpolation sea surface temperature is abbreviated with AVHRR-OISSTV2. So we have this auxiliary information on either side of the acronym, which this introduces complexities and kind of changes the assumptions we can make about how the data set looks. And finally, in this work, we look at, there are some data sets that are so common to the field that they are actually used without definitions. So for example, in these two data set references, in the article, the acronym is never defined, but it's so common that it's assumed the reader will know what it is. And if you're looking for data sets, and you only look for the name, or you assume it will be there, you'll miss these particular references. So after exploring or taking a look at the nuanced ways that we can try to find text references in data, I'm going to share the three approaches we looked at, a couple of revisions, and then where we can go in the future. So approach one is string matching. And in this approach from the author, what they did is they converted the data sets we know we want to find with some documents that we suppose the data sets are in, and we turn everything to lowercase, and we use a substring search to find it. This is very fast. However, you need to know all the data sets you'd like to find ahead of time and all the possible ways they could be cited, which from what we just saw is very difficult to do because there's a variety of ways that authors will cite data sets. Also, by lowering everything or putting everything in lowercase rather, data sets that have clever acronyms that happen to be homographs for common words will introduce false positives. So slosh and herd in lowercase just become common words, slosh and herd. which can mess with your false positives that you see from your model. Technically, you could capture all the kinds of data set references that I mentioned before, but in practice, this would be very difficult for the reasons that we saw in the examples. Seeing the shortcomings here, but the promise of the approach, we restrict the behavior of the model by moving everything to a regular expression. So rather than saying everything is lowercase, we'll say some things can be lowercase, and acronyms, which where casing is important, we'll keep in the uppercase. This maintains speed, but is not as fast as a simple substring search, but saves us from confusing acronyms that have common homographs by ignoring case. The disadvantage, again, to this string matching approach in general is that you have to know all of the data sets you want to find ahead of time and all of the ways they could be cited, which is a hard problem. However, this in principle could find all of the data set forms before, but in practice would be difficult. The second approach was entity classification. I'm going to expand on what that means a little bit. So given a document, this approach says, I'm going to find all of the entities in this document that match the pattern dataset name with an abbreviation, right? So some name with an abbreviation of that name after it in parentheses. I'm going to call all of those entities, and I'm going to use a Cybert-based classifier to classify these entities as either being a dataset or not. The advantage of this approach is that the model learns what a dataset name looks like and what it doesn't look like. And so you don't need to know all the datasets ahead of time. And in fact, you may find datasets you didn't know you were looking for. The disadvantage is that the only entities you'll find are those that satisfy this pattern. You have to have your full name and an abbreviation. And from the previous slides, we saw that that's not comprehensive. So we'll capture some of these, which are common, but we won't capture most of them, importantly, the most generic kind. Our update to that is to, again, relax things and control things a little better with a regular expression. So we use a regular expression to broaden the net, to improve our recall, right? We want to capture more things and lean heavily on the classifier to filter out the things that are not data sets. So this, again, has that same advantage. We have a machine learning model that learns what data sets look like and what they don't look like. The disadvantage is the same as before, that we can only capture things that the regular expression captures. However, that's a much broader net than we had with just the simple one pattern. And so importantly, we capture a common just data set name entities. And finally, this token classification approach, these could be covered by a talk longer than 15 minutes on their own. So I would try to cover it at a high level, but I'm happy to continue to answer questions in the chat after. The submitted approach used a math language-based model. And the idea here at a high level is that it's going to hide the actual names of data sets during training and ask the model to identify data sets by the context that these censored data sets are in. So if you hide all the data set names, the model can only learn how we refer to data sets, not necessarily names in particular. This is actually a really good idea because you can think that even if I didn't know a data set, I would know it was a data set by how it was referred to in the text. For example, if there was a text or a sentence that said, the data we use in our project was from the peanut butter and jelly survey, even if I wasn't familiar with that particular survey, I know they're referring to a data set. And so this is a very intuitive way to go about it. At inference time, though, on unseen documents, we don't know which entities to mask. And so at inference time, this model has to generate large collections of embedding vectors and sample from them. And that gets a little bit technical and complex and can adversely affect performance, or at least make it inconsistent, which is the case for this model. But the advantage is that the principle behind it is good. Models learn how data sets are described. The context matters. The disadvantage is that these sampling strategy you have to use at inference can spoil the results if you're not careful. But in principle, this lets us find a robust set of data sets. We took that approach and we saw the advantage of it, but saw the disadvantage of having to sample from embedding vectors. And so we trained an NER model that also predicts whether or not each word is a data set. This has the advantage too, that it sees the context that a data set is referenced in, and so can lean on the surrounding tokens or words, but also can see the data sets themselves and doesn't have to rely on a random sampling strategy. An advantage of this approach is that it learns to distinguish data sets at the word level. So we can sort of just throw a bunch of text at it. We don't have to worry about designing regular expressions, and it can read the context. A disadvantage is if you're not careful with how you filter out or heuristics you add around the model, you can end up with false positives. And you can see some of those in our article, where things like in science or study may have met a threshold to be considered a positive, but the surrounding text didn't. And so you don't really see the rest of it in context. Again, these could be addressed with heuristics, but is something that you have to be aware of, and is a notable thing about that particular approach. In principle, this approach as well can tackle general data set references because we just feed it all of the data sets. So given that we've seen how data sets are and we've seen some approaches, and I hope I've piqued your interest a little bit, and maybe you've even thinking, these ways are good, but I've got a better idea. And I think that that's great, and I would like you to contribute to this. But the key thing we have to do is be open. And I think I've heard a lot of that in the other presentations, that everything should be open and shared, and we can handle this together as a community. First, we need code. Part of our project was to organize and structure benchmarking and code for models in a way where it's easy to add new models to evaluate different implementations against the implementations from the Kaggle competition and from our article. And so we wanted to make it easy to continue to work. Next, the data has to be open. The Coleridge Initiative competition was great for this because we can all get to the data. Additionally, recently, the dataset mentions detections dataset was also released, and is another dataset detection open dataset that we can all get to and improve on. So we have the code and we have the data. The next piece we need to work on together, I think, will help us accelerate this, is benchmarking. The initial competition worked well for this because people could come together and try to solve the problem in a bit of a competitive way. But we really need a community-based approach. It doesn't put the onus then on a smaller group to sort of maintain and curate the data set, but we can all do it together. And in this way too, if the documents that you curate, you can add and they're well done. And you can also include documents that have data sets you care about. So by adding to the community's efforts, you are automatically sort of prioritizing the data sets you care about, which also improves the data set quality. So I think together we can do this. And I think that with this last key, we'll have a bit of a community-built effort. And with that, I can answer any questions in the Q&A.